Welcome back. We have till now studied the torque experienced by an electric dipole in a uniform electric field and the work done on it in rotating it in the given electric field. Now, I would like to discuss with you what would happen if a dipole is lying in the electric field in the state of stable equilibrium as shown in this figure, and it is rotated by a small angle theta from this state. You will see that in such a situation, the dipole will start performing oscillatory motion. First, let us understand it physically. What would happen to it? Suppose the dipole is rotated and is brought to new position, which is like this one. Then you will see that because of this new orientation, the dipole will start experiencing torque, which is proportional to sine theta. Because of this torque, the dipole will come back to the state of equilibrium position, and because of inertia, it will not stay there. However, it will go to the opposite side due to inertia, and as soon as it goes to the opposite side, the dipole will start experiencing a torque in the opposite direction, which will again bring it back to the state of stable equilibrium. As a result of this, it will start performing oscillatory motion in this field. To understand it mathematically, let us assume that the dipole has been rotated by a small angle theta from its state of stable equilibrium. Then, when it is in such a state, it will experience a torque given by tau equal to minus P into E into sine theta. Here, the negative sign occurs because of the fact that the dipole is experiencing a restoring torque. And we know that if theta is very small, that is, if theta tends to 0, then sine theta is equal to theta. Therefore, this equation becomes tau equal to minus P into E into theta. If the dipole has the moment of inertia I about the axis of rotation that passes through this midpoint of the dipole, and alpha is the angular acceleration produced because of this torque, then tau is equal to I alpha. It means I alpha is equal to minus P into E into theta, or alpha is equal to minus P into E into theta upon I. Now we know that in this case the dipole moment is constant, the electric field is a constant, and the moment of inertia of the given dipole about the given axis is also constant. It shows that the angular acceleration so produced is proportional to the angular displacement and is oppositely directed. This is the condition for a particle to perform oscillatory motion. It means the dipole will now start performing oscillatory motion about the axis passing through its midpoint. In order to calculate the time of oscillations of this dipole, we will have to recall that in a simple harmonic motion, T is equal to 2 pi into square root of displacement divided by acceleration of the particle. Here we can see that from this equation tau equal to minus pe theta, we got I alpha is equal to minus pe theta, which gives us theta upon alpha is equal to I upon P into E. So the time of oscillation of the dipole becomes T is equal to 2 pi into square root of I upon P into E.